I need to remember to share. Okay. Got it. Okay, so yeah, thank you so much for the invitation. I'm very happy to be here and nice to meet. I don't think I know most of you, so nice to meet most of you. And so today I'll tell you about the harmonic polytope, which is doing work with Federico Ardila. But before I get to talking about the harmonic polytope, I wanna talk about, because one of the results we're most excited about regarding this polytope has to do with volumes. The volume of this polytope. So I want to take a little detour and talk about volumes. So suppose you start with a finite set. Then you ask yourself, well, what is the volume of the convex hull of this point? You have a lattice polytope. And well, and of course, well, I think people here really care about polytopes and well, they're great. And one of the natural things to ask is like, okay, dimension, number of vertices, and the volume is one of the things that is natural to ask about it. And so a strategy that works is to, well, triangulate it and add the volume of each maximal simplex, because computing volumes of simplices is easier. And so you can apply this strategy to find the volume of your polytope. But in practice, this strategy is not very feasible because, well, back in the 80s, Dreyer and Fries showed that computing the volume of a polytope is sharply hard. And so what this means in case, well, I don't know, like this is a measure of complexity and comparing it to other type of problems, this is as hard as computing the permanent of a matrix. So this is not an easy problem from a computational point of view. So this motivates having formulas for families of polytopes, because then you don't have to compute, you don't have to do this computationally complicated problem. And it also tells you that probably this is not going to be that easy. So this paper that I have here is called, I like the title, is Computing Volumes is Hard. So that is the feeling of what is going on here. So that also tells you that knowing different ways to compute volumes of polytopes is useful. So you shouldn't just be satisfied with triangulation. It will be good to know other ones. And so there is an approach using polynomials. And so that the main tool there is the Newton polytope. So you start with a polynomial on n variables, and well, okay, it can be all around polynomials. So yeah, I can tweak this because I think I do that later. So you can take your polynomials can have a positive or negative exponents as long as they're integers. And what you do is you take the Newton polytope to be the convex hull of the exponents that have non-zero coefficients. Okay, so what, like in this very simple example, if you start with this polynomial, you take the exponent vectors. So this is the exponent vector for 1, this one is for this one, and 2, 0 is the exponent vector for x1 squared. And you ignore the coefficients, and you take the convex hull of those 3 points and you obtain this triangle. So given a finite set of lattice points, you can construct from it, like combine all the polynomials that kind of are relevant for the convex hull of this point, or for this point, well, not necessarily a convex hull, but for this point. So I construct this vector space that is the set of polynomials where the exponents, you only take them from this finite set. And the coefficients are complex. So this is a vector space. So yeah, so for example, this polynomial is in the vector space for these 3 points. And so using this, we obtain the following theorem. So in the mid 1970s, Bernstein, this is like the Russian schools, or Bernstein-Khovanskii-Kushnirenko, I'll tell you 2 versions of this theorem. They were studying subvarieties of C star to the n. So looking at solutions to systems of polynomial equations in C star to the n. And they realized that these Newton polytopes play an important role when you want to count the number of solutions, for example. So for a generic choice of points in this vector space, so you just basically pick the coefficients at random, the number of solutions to the system of equations in C star to the n, so none of the entries are allowed to be 0, is n factorial times the volume of the convex hull of A. And as a sanity check, here, this is a very simple example, but is just so we can check that this makes sense here. Well, the volume of this polytope is 1, and you're multiplying it by 2. So you would want like this number is going to be 2 for that very simple example. And in terms of polynomials, you're looking at this is a quadratic formula, so you're intersecting two quadratic formulas. Indeed, they intersect almost all the time in 2 points. So this is what this theorem is telling you for that very, very simple example. Okay, so here, so now this is the first version, and to be honest, like I feel like this type of theorems were usually thought as a development of how, look, we can use polytopes to understand the algebraic geometry features of a system of polynomial equations. You know, that was the theme when it began, and for a long time it has been seen that way. But Poznikov, and I'm not sure if he was the first one, but indeed he's whose work I'm most familiar with. He thought about it, well, we can do it the other way, because solving system of polynomial equations sometimes can be easier than computing a volume. So can we go in the other direction? And the answer is yes, we can go sometimes in the other direction. So in this case, and he did this for a family of polytopes called generalized permutahedron. So let me start with the permutahedron.
I'm sorry, just before saying that.
Yeah.
So what do you mean by generic choice of the polynomials?
Yeah. So I mean that I pick, so this is like a vector space, right? So this is isomorphic to C to the, I don't know, to the size of A. So I just want to pick the coefficients to be like inside a dense subset of that vector space. Or in other words, they're picked at random.
Thanks.
And not random would be like, of course, a non-random choice would be if I wrote this polynomial twice, that would not be random, and then the theorem wouldn't hold, right? They intersect at infinitely many points.
I'm sorry to interfere, but I should say that actually there is quite an explicit expression for like what it means to be like generic. So there are conditions that should be satisfied. I mean, it's just so it's kind of I would say the most important part of this theorem, basically being able to say to tell which are generic, and it's crucial to using this. Yeah, so sorry.
Yeah, no, thank you. Good. Any other comments or remarks or questions? Okay. So for the permutahedron, yeah. So let me get back to it. So what the permutahedron, just in case you have never seen it, is the convex hull of, so you start with the vector 1 up through n, and you permute it. You take all the n factorial permutations of that vector and you take the convex hull of that polytope. So here I'm giving you 2 examples. This is when you take n equals 3, you get a 2-dimensional polytope in R3. And when n is equal to 4, I took this picture from Wikipedia, and you end up with this 3-dimensional polytope in R4. And okay, so we want to compute, well, it is known that the volume of this polytope inside its affine span has been known for long time. But let's suppose we want to do it ourselves. This one can do it by triangulating, lots of different strategies, but let's suppose we want to compute it using this, like using polynomials. Okay, so if you wanted to do that, then it's useful. Well, here it's a little bit hard. I mean, one could, like, if one were to use the version of the BKK theorem I told you, then you would have to write a polynomial, for example, for this one with six terms. And so one can do it, but it's really not the right point of view. The best point of view is to write it as a Minkowski sum. So here we have that the permutohedron is always a translation, and this is not a conventional notation, but I'm going to have a big mixed volume, so I'm trying to make things concise. So I'm going to let EIJ denote just an interval. It's a convex hull of two standard vectors. So if you add them together, you end up with basically the permutohedron. And the translation part is not too, it's just, it's just rather you would end up with subtracting 1, 1, 1 from all of your points. So it's not the translation part is not too important. But since it's a translation, computing the volume of this Minkowski sum is the same as computing the volume of this permutohedron. And now we can see how a different version of the BKK theorem can give us an answer using volumes. So before getting to that, there's I need to tell you about mixed volumes. So Macmillan came up with this function called the mixed volume. So there's a unique function that goes from n tuples of polytopes in R to the n to R, which is called the mixed volume function. And what is the key property about it? That for any m polytopes and non-integer coefficients, well, if you scale each of your polytopes by these coefficients, and then you take the Minkowski sum of those scaled polytopes, then when you compute this volume, you can expand it in this way. So no matter what your coefficients are, you can always expand it in this way, and then using this mixed volume function. And there are other properties that the mixed volume function satisfies, like for example, it's symmetric. And that's sometimes you might see it differently. So if I listed here, these are all tuples, but if you listed it, if you wanted to list them in ascending order, you could do that, but then you would have to multiply it by some factorial in front. Okay. And so here, okay, so applying that to our permutohedron, remember we said this is the case. So the volume is equal to the volume of this Minkowski sum, which is equal to this, okay, so in this case, all the lambdas are 1. And so using this mixed volume, I can just write it as the sum of mixed volumes. And here, this n minus 1 is because, remember, I'm computing the volume inside its affine span, because it's not full dimensional, so I have to do it there so that the volume is not 0. So the second version of the Bernstein-Khovanskii-Kushnirenko theorem is that, well, if you start with, now it's not only one set, I want n different sets of lattice points, and I'm gonna let Q denote the convex hull of each of them. Then again, this genericity that is important to be precise about, but I don't want to get into it here. For a generic choice of polynomials, where each of them is in this vector space that I said before. So namely, the exponents of each fi are chosen from the alpha i's, and then the coefficients are random, are chosen at random. Then the number of solutions to the system of equations, where none of the entries is 0, is now n factorial times this mixed volume. So yeah, it depends. One could argue that I really didn't define the mixed volume for you, although this property up there does define it. And to me, I do think about polynomials a lot, well, often. So to me, this seems like a concrete definition. So if you want to, you can think of this as being the mixed volume. Although you could also argue, well, you didn't tell me what generic is, so okay, well, fair enough. But okay, so here is how we can use a Bernstein-Khovanskii-Kushnirenko to compute volumes of polytopes. We can write a polytope as a Minkowski sum, and each of them, for each of them, looked at the mixed volume by computing the number of solutions to a system of polynomial equations. And in this case, notice that if you okay, so if you look at, what do I want to say? Yeah, so for in this case, each AI is going to be, or I don't want to call it, well, I don't want to label it, but each of the A's are going to be EI, EJs. Okay, so in this theorem, like if I want to apply this theorem to the permutohedron, my A's are just two standard basis vectors, and then the F, our polynomials, are just going to be xi plus, oh, I should put coefficients in front. Ci xi plus cj xj. Okay, so these are the equations that I'm trying to solve. So it says, so if I wanted to compute this volume using this strategy, is just looking at the number of solutions to a bunch of linear equations, and they're not only linear, they're just sums of two terms. They're really, really, really simple equations. And okay, there's a little remark that okay, so here we have to be, I mean, this works no matter what the dimension of your polytope is, but if your polytope is not full dimensional, if your polytopes are not full dimensional, or yeah, if your polytopes all live in an affine span, then you might not get interesting answers. So the way, but you can always fix that using linear algebra or quotienting by spaces. So in this case, for us to get the right answer, since our permutohedron lives it's not full dimensional, I need to count some number of solutions, not in C star to the n, but in this space. That is so that I'm in the right vector space. And that is very simple. You can just choose some of the variables, like you choose x1 is always going to be 1. That's how you can count this. So using this, one can prove, so as I said before, it was very well known that the volume of the permutohedron is this. It's the number of trees within vertices. But using this strategy, one can actually see the proof because, well, remember, I'll write it here again, but my F's are always like Ci xi plus Cj xj. So from here, you can construct a graph where you connect I and j for each of the variables that appear. So for each polynomial, you have these two terms, and so for each polynomial, you can construct. I didn't want to erase. You can construct an edge. That edge connects the two variables that appear in that polynomial, and then you see that system has a solution if and only if it forms a tree, and that's how you can prove that this is the case. Okay. And so, and Poznikov used this proof to come up with volumes for a class of generalized permutohedra. So he used this to compute volumes of Minkowski sums of dilated standard simplices. So instead of so what we did before was taking the convex hull of EI, EJ, it was only intervals. Now we're gonna take convex hull of E1, E2, E3, E7, E8. So those type of simplices, and you dilate them by some coefficients. So it's a much more general class that forms a subclass of generalized permutohedra. So he did this. Okay. So yeah. So before I move on, this is like an overview of maybe using, or a short summary of how one can use like BKK to compute volumes of polytopes. But yeah, if there are no questions, I will move on to the harmonic polytope. Okay, so what is the harmonic polytope? So for that, the harmonic polytope is going to live in R2n, but I do want to split it into two parts of R. And I'm gonna fix a basis for the first R to be E1 up to En, and for the last R to be F1 up to Fn. And I'm gonna label the coordinates by X, Y. Okay. And so what is the harmonic polytope? I'll write it as a Minkowski sum. So what it is you take a product of two permutohedra, and then you take the convex hull of this. This is like you can think of this as a twisted simplex in some sense, something like, and not too important by now, but I'll denote it by delta later. So here I have the example. This is H22. because it's the only one I can draw. The next one leaves, yeah, this is going to be 4-dimensional, so I'm in trouble. But okay, this picture looks like a permutahedron, but it is not. Here, like for example, this one, and I'm writing it in 2 levels just to save space, because otherwise it will be a vector of length 4. But yeah, for example, this one, you can see that here you're taking 2, 1 for the first permutahedron, the point 2, 1 for the first permutahedron, 2, 1 for the second permutahedron, and then you're adding 1. So for this first one, you get 3, 1 by taking this 2, like this vertex of the first permutahedron, vertex of the second permutahedron, and E1 plus F4. And you do that for all of them, and you end up with this polytope. Now, a good question is to say, well, is this a generalized permutahedron? So, this is a sum of standard simplices. Now, this is not a sum of standard simplices, or this is not a standard simplex, but well, it could still be a generalized permutahedron. And if it were, well, we could throw at it all the machinery that Poznikov developed. But it is not. It is not a generalized permutahedron, but it's very close. It's close, except not exactly. But let's start discussing what we know about this polytope. So we do have a formula for the F vector. It's a bit technical, so I won't get into the details of it. But in particular, the number of facets is 3n minus 3. And the number of vertices is n factorial squared times the nth harmonic sum. So we liked this formula for the number of vertices, so we decided to call it the harmonic polytope because of this. So now to discuss the volume. Okay, so as I said, well, as we see here, this polytope up here lives in R4, but it's 2-dimensional. So it is in general the case, it's not full dimensional at all. It always lives inside this space. So it lives inside, or the affine span of this polytope is this affine plane. That, yeah. Oh, I put a square there, right? It's just trying to save space, but it's L cross L. So it lives inside. So the dimension, as I said before, is 2n minus 2 always. So we want to compute the volume of this polytope inside this affine space. And to do that, well, remember we said the harmonic polytope is the product of 2, well, is the sum of this twisted simplex plus the product of 2 permutahedra. So I'm just going to write each of those permutahedra as the Minkowski sum of some line segments. And again, I guess here I'm using, this is a little, I'm using hats or bars on top of my i's and my j's. Just again, here is not too important. You can ignore them here, but eventually we will have mixed volumes and there will be sequences of f's and e's. And so to avoid too many indices, I'm doing that. So to compute the volume of this polytope, well, we just need to look at sums of mixed volumes where we're picking some of this polytopes or intervals, some of this polytopes, and some of this. And there are going to be repetitions that is allowed. So what we have is we're going to have that the mixed volumes are going to be, you choose R of the first type of simplices, S of the separate, intervals. R of the first type of intervals, S of the second type of intervals, and then you fill in the rest with that twisted polytope. And you want to have in total 2n minus 2, many of them. Okay, now each term, you can construct a bipartite graph, a bipartite multigraph gamma. So for example, if you look at this term, that it does satisfy this form, right? I have 3 of the E type, 4 of the F type, and 3 twisted simplices. Then what we will have okay, so I'll construct that graph as follows. So I start with this black piece. I always start with it. And then you should think that up here you have the E's and down here you have the F's. And with that in mind, okay, so then this 1, 2 up. This 1, 2, you connect these two vertices in the E's level because you have E1, 2. Then E3, 4 tells you to connect this two. E5, 6, you connect this two, and you're done with the E's. And now the F's tell you what to do down here. And if you follow the same rule, you end up with this 4 edges. And now you just contract those orange edges, and you end up with this graph. That is a bipartite multigraph. Now, this here, from this bipartite multigraph, there's this well-known object, well-known toric ideal. So by a toric ideal, I just mean a prime ideal generated by binomials. So by polynomials with exactly 2 terms. And the way you construct this toric ideal is, well, for each fundamental cycle of your graph, it's always going to have degree 2. You can just like, okay, so, you know, you can travel it however you want and say, okay, so first you go to a 1, then you go to a 4, then you go to a 3, then you go to a 2. And think about the even steps you took and then the odd steps you took. So here, you first went to the 1, that's an odd step. Then you go to the 4, that's an even step. Then you go to the 3, odd step. Then you go to the 2, even step. And that's how you obtain this binomial. And then the other one, you have this fundamental cycle. And that leads to this. So this is a toric ideal. Okay, so now so this is a well-studied class of toric ideals. It's called like an edge toric ideal. And well, here is what we observed. So basically using BKK, and I'll say just a little bit more about that. But one thing we observed is that, or we showed is that, well, if you look at the degree, okay, so toric ideals, they're called toric because they cut out toric varieties. Okay, and so, and they cut them out, they give you an embedding. So just as the volume is an important number to know about a polytope, the degree is an important number to know of a variety, something you can compute. And the degree of the toric variety for this ideal is 2. So we showed that this mixed volume is also going to be 2. Okay, so let me state our theorem. So each mixed volume in the expansion for the volume of the harmonic polytope, like in terms of those intervals and the deltas, equals 1 over 2n minus 2 factorial times, the degree of the toric variety cut out by the toric ideal of the associated multigraph. So this is the precise statement for what we have up there. Okay. And I'll say, okay, so what is the strategy to show this? Well, what we did was we honestly used BKK to write a system of polynomial equations. And we have a bunch of equations that are like as before, like, right? We have some equations of this form because those correspond to the intervals. But what made this problem interesting was that, okay, so this corresponds to the interval EIJ, or if excess, I want to use EIJ. But if you look at this delta, well, this delta was the convex hull of EI plus FJ, for EI plus FI, sorry. And so when you construct the polynomial for that, you're going to have, okay, so C1, X1, or let me call it D1, X1, Y1, blah, 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 up to Dn, Xn, Yn. Goes to 0. That is the polynomial you're gonna get. So this is no longer a system of equations with only linear terms. Like if it were still linear, but maybe one of your terms were longer, it would still sound okay, but we went to a system of equations where some have degree 2. Okay, so this made the problem much more interesting. But the way we got to this Tauric ideal was simply by like eliminating some variables. So this process that we did here, if you think about it, like I mean, when you think about this is more or less telling you that xi should be equal to xj modulo some constants that are chosen randomly. And honestly, that's what we're doing here. We said, well, x1 plus x2 equals 0. So basically they should be equal. So we can eliminate one of those variables. So using elimination is how you can end up with this ideal. And then like just this degree gets preserved through our operations, in particular eliminating, and that's how we were able to transform the problem of finding solutions to system of equations to computing the degree of this Tauric variety. Okay, and so putting it together, we end up that the volume of the harmonic polytope is equal to this. It's an expression. It's a closed formula. You know, you're summing over connected bipartite multigraphs with n label edges. So this is what the sum is over. This is that degree I was talking about. And here we're dividing by this factorial where this is the number of vertices of your graph. And yeah, for each term, we're multiplying it by this. Okay, so that's our formula for the volume. But of course, like this is a Tauric variety. And well, if you're not like, okay, if you have heard of Tauric varieties, people always say, oh, well, the geometry of a Tauric variety can be understood in terms of the geometry of a polytope or something. So really, we should be able to say this in a different way. And something that is almost immediate is there is a polytope associated to this variety, so you can transform this degree into the volume of some polytope. But that volume can be computed in a better way, and this is something that polytope appears in the work of Poznikov, and he was able to, well, we were able to use work of Poznikov to translate computing this degree into a polytopal count. So the degree of this variety is equal to the number of lattice points of Poznikov's trimmed generalized permutohedron P gamma minus. And so let me tell you a little bit about just in our example, what I mean by this. So here, in this case, we have that, so we have, this is our graph that we had before. And I'm labeling the vertices because I need to construct the trimmed trimmed generalized permutohedron. So what I do, it's always, I mean, they form a little bit of a bigger class than generalized permutohedra. You just basically, these objects are simply, you take a generalized permutohedron and you subtract no, I shouldn't use that notation. You subtract the standard simplex of its ambient space. You do the Minkowski sum of these two objects. So, but he specialized them. He has more to say when you can construct them from a bipartite graph. So what are those in this particular case? So what you do is you construct it by taking, so these are, even though I didn't label them, these are the bosses of the polytope. So here, this one, you just look at the convex hull of the E's that are its neighbors. So these three are the neighbors of this vertex. So that's why I got this term. You add this other one, because from this point of view, you just look at its neighbors. So you end up with this other simplex, and then you subtract the simplex of its ambient space. And in general, you don't always get that lucky that this appears as a term, but even if it doesn't, you can do the Minkowski difference. That will be fine. So in this part, but for this very concrete case, when you do this trimmed permutohedron, trimmed generalized permutohedron, you end up with this interval that has two lattice points, and it agrees with what I have been telling you before. And in Polytope has some way of computing the number of lattice points of his stream generalized permutahedron using some draconian sequences. Okay. Okay, so then what I want to move on to next, once that we know its volume, is I want to talk a little bit about its phase structure. So a little bit more about the combinatorics of this polytope. Okay, so for that, let me tell you, let me move this. I was going to move this, but I forgot. Let's ignore that L for a little bit. Oh no, that's going to be a bad idea. Yeah, let's ignore that for a little bit. Okay, so let me start. I want to now go and tell you the phase structure of, like, give you a combinatorial label for the phase structure of the harmonic polytope. So for that, I'm going to start with the following moduli space. So I'm going to start with n tuples of points in R2, modulo common translation. And so I want to be able to talk about points in there. So if I want to accomplish this modulo common translation, the way I accomplish it is by, or one way to accomplish it is by taking this diagonal line and then like, you know, even though I'm moving the line, you should be imagining I'm translating all the points. It's just that I cannot really do that. It would be a mess. So I'm moving the line so that it touches until all the, like, I want to start with the line maybe like so that all the points are on one side of that line. And then I move it until it touches at least one of the points. In this case, it touches two. Okay, so that's how I fix this modulo common translation. And I can just think of points that are on one side of the line. And I'm going to stratify this vector, this moduli space by taking, and the way I'll index this data is by recording three things. So first, I'm going to let K be the set of points on the line. So in this case, we have that 2 and 6 are on the line. And then I'm going to take a partition Px that what I do is for each of my points, including the ones on the line, I do a horizontal ray until it hits my diagonal. And I write where it hits the points that hit that. Yeah. So here I have a 1, here I have 3, 5, here I have a 2 and a 4, 6. And I made the horizontal ones orange, or yeah. And so what I do is I go from right to left and take note of what I see on my line. So first I see 4, 6 together, then I see a 2 together, then a 3, 5, then a 1. So I obtain this partition. And then I repeat the same with these vertical projections, but I read them in this way. And this is just a convention. Yeah, it's easier to axiomatize what's going on if you do it in this convention. But yeah, so I go in this direction and in this direction. And so here, notice that vertically you have the partition 1, 2, then a 6, then a 3, and then a 4, 5. So if I combine all, like for this example, if I can combine all the all the n tuples of points that lead to these three pieces of information. And I'm gonna call these three pieces of information harmonic triples. And in our paper, we have an axiomatization. So we tell you what properties K, Px, and Py need to satisfy. But this is one way to think of it, a non-axiomatic way to think about what they are. So this is what a harmonic triple is. Okay, so what role do they play? Well, the phases of the harmonic polytope are in bijection with harmonic triples on N. Okay, so here we have, and this is not that the lattice point is counted by that. I don't know why I have that lattice point there. But anyways, this corresponds to the interior. Okay, so here I have all the phases labeled by the harmonic triples. And in particular, we have that the harmonic polytope is cut out by, well, okay, this one we had seen before, or I had told you before, this is being on that affine plane. And here are where the facets come to play. It's given by these inequalities. So it's like the details of what this is not as important as the fact that you have one inequality for each pair of non-empty sets where both are not equal to n. One of them could be, but both should not be. Like, for example, here, S is everything, but, oh, wait, did I want that one? No, I scratched that. No, ignore what I just mentioned, but I do mean this. For each pair of non-empty sets, not both equal to n, such that their union is everything. So you can obtain okay, so this is where, well, like, you can use this type of sets to get all the harmonic triples that lead to facets. And if you count them in this way, you get the 3n minus 3 that I mentioned before. Okay, so now to end, I want to talk a little bit about where did this polytope come from. So it seems like, okay, you just told us the story about the polytope and how to compute its volume. And I personally like the volume computation a lot, but yeah, this where did it, it's not like, oh, let's come up with a polytope whose volume computation could be interesting. That's not where it came from. It came from some work by Ardila with his collaborators, Denham and Hu. So here, and here, I'll guarantee there's people in the audience that know way more about the details of this, but I want to give you an overview and maybe highlight parts where this polytope, where polytopes played a role. So I'm gonna start with a matroid on n elements. So this is the of rank k, and then, well, some like an invariant of that matroid is its characteristic polynomial. Okay. And so, yeah, so many things that you can say about it, just very, very briefly, like if your matroid corresponds to a graph, then this is the characteristic polynomial graph theoretically. And there's two numbers that you can extract from this polynomial. So the first one is the f vector, that what you do is you list for each, in degree by degree, the absolute value of the coefficient. So you go ahead and list that. And this one, if it turns out that if you do that, if you write like, okay, so a matroid has flats, and those flats, if you organize them, you can construct a lattice of flats. And so if you count how many flats you have of each rank, that's another way of getting the f vector. And then the h vector is similar, is just instead of listing the coefficients of this one, you list the coefficients of this other one. And this is a standard thing in algebraic combinatorics, going from f to h. So as I said before, people here I know are familiar with this because like this is a very, well, I mean, we all are, because it's a very beautiful result in combinatorics recently. So this is it was a very old conjecture that this sequence, the f vector, is log concave, right? So this is a beautiful theorem that proves a really old conjecture, and the proof develops some beautiful machinery. So what do I want to highlight about the machinery that they developed? So first, of course, their machinery called combinatorial Hodge theory. And this machinery was inspired from like what they could do for representable matrices. Okay, so they used their intuition from the case of representable matrices, where you have algebraic variety, to define a combinatorial object, which is the Chow ring of a matrix. And the key object in defining this Chow ring was the Bergman fan of that matrix. Okay. And so this is a fact the Bergman fan of your matroid is the tropical linear space associated to your matroid, which is a polyhedral object, intersected with the normal fan of the permutahedron that I mentioned before. So, and let me denote this by. So the normal fan of the permutahedron is also called the braid arrangement, but here, this is a, I don't know, maybe I'll spend too long on it, but this, because this will be important for what I will say later, that, okay, so this is a simplicial fan, and here you have a fan that refines all the Bergman fans of a matroid when you fix n, okay? So that is a very special object that you have here. So in this case, of course, these results are deep and interesting, but they did have something working for them, that there was a Bergman fan that already existed, and that you have this innocent looking braid fan, or the normal fan of your permutahedron. So you had those things and they exploited them beautifully to prove this conjecture. Now, a stronger conjecture, because this implies that this sequence is log concave, was more recently proven by Ardila, Denham, and Hu. And so this sequence is also log concave, and it was conjectured in the 80s by these mathematicians. Now, what strategy did they have? Well, they wanted to carry a similar program that they have here, but this program couldn't be carried without first having a geometric intuition. Like, you needed algebraic geometry to help you inspire yourself of like, what are the right objects that we want to define? So in this case, for this situation, so when you have a matrix that is representable over a field of characteristics 0, so Junho identified like the right variety. So this is the Varchenko's variety of critical points, and inside there you can use Hodge theory to prove that the H vector is log concave in the representable case. So then they had, and this Varchenko's variety of critical points arises in Lagrangian geometry. Okay, so in that case, that was key, that gave them inspiration. So they were able to recognize, like they analyzed the features of what was going in that representable case to try to come up with features that could lead them to define the right objects for this conjecture. Okay, so they still want to use combinatorial Hodge theory, but they need a Lagrangian analog of the Bergman fan. So they did define it. They defined the conormal fan of a matrix. And given this object, they needed to define the Chow ring of that object. Okay, and this is where like polytopes came to place, because just as we had before that the Bergman fan was the intersection of the tropicalization with some simplicial fan, they also wanted to accomplish it this way. And the simplicial is important so that so that they can actually do computations in here. But okay, so this is known, okay, tropical geometry or tropicalization of matrices, or tropical linear spaces indexed by matrices are developed. This is not, it's unclear what that would be. So what properties did they identify that this fan should have? Well, it should be simplicial. And it should satisfy that if you take this fan and you project onto the first coordinates, you should get the normal fan of the permutahedron. Similarly, if you project to the latter coordinates, you should get the normal fan of the permutahedron. And that should be a map of fans, meaning that it's not just, yeah, it's taking cones to cones, like rays go to rays, the span, yeah, it should be a map of fans. And similarly for this one, they needed this map that is a little bit different. So here I'm going to take the normal fan of this standard simplex, and you take x comma y mapping to x plus y. That should also be a map of fans. So they needed those properties. They identified those properties from the algebra, from the representable matrix case. And then the last one that they needed was, not only should this fan be simplicial, but it should be the normal fan of a polytope. Okay, so this is somewhat ambitious to get. Like, I don't know, like even just having a fan, like knowing if a fan is the normal fan of a polytope can be difficult. And so here it's, yeah. And here it's even more ambitious because you get to refine your fan until it's a polytope, but then like you need to have done it well. So this normal fan of my harmonic polytope almost works, but there's a really sad thing. It's that it's not simplicial. So you can still define this situation here, but computing is very hard. So it's very undesirable to go ahead and carry a program with a non-simplicial fan. But it is universal or canonical in some ways that any fan satisfying those desired properties must refine the normal fan of my harmonic polytope. And so a polytope, they had to work really hard, but they came up with some polytope that satisfies the properties, which they call the bipermutahedron, and it is cut out. So you can look at like either their original paper, and they have one on the combinatorics, and Federico has one on the bipermutahedron. But just to give you the inequalities, it is cut out by this. Well, it has the same dimension as a harmonic polytope, and it's cut out by almost the same. Well, it's cut out by the same number of inequalities. They look different, but they have the same number of facets. So, but this one is better because it's simple. And so just, yeah, I'm basically done. I just wanna say a few more things that, well, first, of course, they mentioned this, they're honest that they use it by bipermutahedron because it's the one they were able to come up with that worked. But are there other ones that work? Like, can you refine this fan to obtain a polytope that is simplicial and that satisfies the desired properties? And like, because this polytope is very nice, but it has some difficulties to it. And then the second thing I want to say is that so their work, like, in what context does the harmonic polytope arise? Well, this work of Lagrangian, I call it Lagrangian combinatorics. It's leading to new objects in combinatorics that we have not thought about, that have the chance to be very beautiful and exciting to think about. Because remember what I said up here, that here some of the objects that were used to prove this conjecture had already been studied, like, and including like this beautiful fan, this like the permutahedron has been very deeply studied. And that is not the case when you look at this story. So like, what sort of combinatorial objects or can you find, what properties do they have? All of that are very good questions that can lead to some nice objects being discovered. But yeah, that is all I have to say. So thank you so much for your attention.
All right, thank you very much for that talk. Do we have any questions? That doesn't seem to be the case. So yeah, thank you again, Laura, for giving a talk.